Cool. Okay. Hey, everyone. It's super nice to be here. Super nice to be invited to talk about this stuff. I always feel like this is super niche research, and so it's really cool to see so many people turning up to hear about what I have to say. I hope it's interesting for you guys. Yeah, sorry. So I'm Drummond McCulloch. I work at the NRU, the Neurobiology Research Unit in Copenhagen. This is the building which I'm privileged to work in. Yeah, and I'm going to be talking about what I call navigating chaos in psychedelic neuroimaging, and you'll see that that's a bit of a shitty pun going forwards. Just a quick conflict of interest declaration that my PhD stipend was paid for by this big lump of money that I got from Compass Pathways. They're not associated with the research I do. They don't tell me what to do in any way, but they did very generously pay for my entire PhD. So I'm grateful for that. Okay, so first, I want to start by just framing the overall question, which is why do we think it's important to investigate what the effects of psychedelics are on the brain, especially? So I want to just for a second imagine a sad brain, say someone with depression, someone who's in a state where negative emotional stimuli cause them to have disproportionately negative reactions, for example. Over the course of 6 to 8 weeks of administration of a drug like sertraline, about a third of people will move towards a state where their brain exaggeratedly is glittery and shiny, and by that I just mean has the normal response to affective stimuli. But we can also get to a place where the brain is in a really positive state of affective response by giving someone a drug like cocaine. And within about a minute, someone can go from having a very negative thought patterns to having really positive mood. The problem is that about 15 or half an hour, 15 minutes, half an hour later, they go back to this stage of really negative mood, and in some cases, even more negative mood. And sort of orthogonal to that, or perpendicular to that, we have these psychedelic drug effects. You have someone with depression, they get psychedelics, and they move into this totally different brain space where their brain is working in quite a different way. And then, ironically, or not ironically, I guess, instead of going back to being more depressed, you might expect that someone has a high degree of connectedness, and then they would go back to feeling very isolated, the central irony of pharmacology. Like with cocaine, you get a lot of mood and energy, then you have deep reductions in mood and energy. But in this case, people return, but instead of returning to the depressed state, they return to a brain state categorized as low depressive scores. And this is what's been shown in all those clinical trials. So what this is interesting then is what is this brain state? Like what is happening that means that when people go from A to B, they go to C instead of going back to A or to a different place. So that's why I think it's interesting to evaluate what this transition, I don't know if you can see my cursor, is here. Okay, so this is not a new idea. I'm not the first one to propose that we do this. In fact, about 70 or even more studies have looked at what the effects of psychedelics are on acute brain function. Most of them have looked at the acute effects because they're the most powerful effects, the easiest to see a signal, and they're possibly the most interesting. And we published a review in this about this in a journal called Neuroscience and Biobehavioral Reviews. And I've then subsequently updated this figure with all the red ones that have come out in the last 2 years. So it's a really big field, it's a really active field, and it's very exciting in a lot of ways. However, we're very limited in something called replication, which is when you try and apply exactly the same methods to a different data set and see whether the findings from the original data set hold. So if this was a drug discovery pipeline, you would say that we're still in what's called phase one. So we're in an exploratory phase, we're not in a confirmatory phase. With that said, we do have some emerging hypotheses coming out. And today, as you can guess from the title of the talk, I'm going to focus on the brain entropy or the entropic brain hypothesis. So yeah, just to summarize where we are, I really like this table as a description of like doing good science. We've not done any what's called reproducibility, which is where someone takes the same data and the same analysis and make sure that they get the same results. That's not something that we do so much in psychedelic neuroscience. We've done a tiny, tiny amount of replication. Shout out to Katrin, who is one of the two people who has done some replication in this space. There has been some robustness, which is when you take the same data and apply a different analysis to it. And there's been quite a lot of what's called generalizable findings, where people take new analysis frameworks and new data and try and see whether the sort of general core of what they're trying to work out is the same. But the generalizability is the loosest of the sort of replication world. Okay, so we're focusing on the entropic brain hypothesis. This is something that was put forward by Robin Carhart-Harris in 2014. He released this paper, The Entropic Brain, A Theory of Conscious States Informed by Neuroimaging Research with Psychedelic Drugs. I also think this photo of Robin is hilarious because none of that makes any sense. Anyway, he released another paper 4 years afterwards called The Entropic Brain Revisited, and I'm also led to believe that there is an Entropic Brain 3 coming out soon as well, where he's revisiting the hypothesis. But let's take verbatim what he said and what the entropic brain hypothesis is. I'm going to go through this word by word, which feels a little laborious, but it's because we're going to break it down in the next couple of slides. So he says the qualia, or subjective quality of any given conscious state, and specifically the richness of its content, can be indexed by a quantitative measure of the magnitude of entropy, brackets, in the information theoretic sense, in a given parameter of spontaneous brain activity. All right, that's a lot of words. Let's break it down. So let's start by entropy, right? Entropy. I think we all have a sort of idea of entropy as just like chaoticness or busyness or something like this, but it comes down to three key principles. The first one is diversity, so how many different things there are in the system. The next one is unpredictability, taking a sort of temporal dimension into it. How much does it change moment by moment? And the last one is complexity, and that's effectively how much information does it take to describe a system? Sort of a square is a square, a perfect square is a square, but a rose petal, for instance, would take a lot of information to describe. It's a very complex system. It has higher entropy. So this is a conceptual understanding of how entropy works. But what Robin actually said was entropy in the information theoretic sense. So we go to the father of information theory, Claude Shannon, who put an equation on entropy. And so the entropy of x, h of x, is equal to the sum across a histogram of probabilities. Let's not get too much into the weeds on it. Let's use a simple example. So imagine we have a system that has 5 different weather states, or a system like the weather that has, for example, 5 different states. We could say that in California, it's sunny 90% of the time and it's cloudy 10% of the time. This is a simple, predictable, stable system. Where I live in Copenhagen, the weather is diverse, it's unpredictable, and it's complex. It's snowing 20% of the time, it's sunny 20% of the time, raining, cloudy, and windy. And that was just today. So in how we quantify this mathematically is you take the height of each of the boxes. I've just removed all the zeros because there's no point doing that. 0 times log 2 of the height, 0.9 times log 2 of the height of this one, plus 0.1 times log 2 of the height of this one. And so you can say that according to this model, the weather in California has an entropy of 0.47 bits. And we repeat the same thing, but for the weather in Copenhagen, and you can see that the weather is 2.32 bits, and this is a much more entropic system. Okay, and then what Robin says is a given parameter of spontaneous brain activity. And previous work has employed EEG, electroencephalography, and fMRI. For the sake of today's talk and for the paper that we wrote, I'm going to focus on fMRI. Mostly because that's where most of the research has been done. So there's been 12 different papers that have evaluated fMRI brain entropy around the psychedelic experience. And a lot of these papers are very high-profile papers in the space. Dynamic coupling of whole brain neuronal and neurotransmitter systems, enhanced repertoire of brain dynamical states during the psychedelic experience. If you guys have been in the space for a while, you might have seen these floating around. The thing is, and this is sort of one of the key takeaways of today, is that every single one of the quantifications that they employ are totally different, at least mathematically speaking. But I hear you cry, wait a second, didn't you just tell me that there's like a fixed equation for how to quantify entropy? So now how can you tell me that there's 12 people doing it differently? Well, it's to do with how you evaluate your system. So I said before that we were evaluating the entropy of the weather by looking at the different weather states, but we could also look, for example, at the entropy of the temperature, right? And there you can see that you get a histogram with your temperature ratings on the x-axis and how many times it happens on the y-axis. And you can see that you can interpret it this way, or perhaps rainfall or perhaps wind speed. So there's a lot of different ways that a system can be broken down into a distribution, which you can then evaluate the entropy of. Okay, ridiculous slide transfer. So what did we do? We looked at all of those 12 different papers. And we really dug into the methods, and we wrote to the original authors, and we tried to work out exactly down to the line of code what they did. And we found these 12, actually in the end 13 different entropy metrics. And then we wrote the code line for line, and we wrote to each of the original authors, and we said, hey, is this correct? Is this exactly what you did? And once we got a yes from all of those original authors, we took all of those entropy metrics and all of this code in MATLAB, and we turned it into what we're calling the Copenhagen Brain Entropy Toolbox, where it's now a very implementable way of applying each of these entropy metrics, and it's available on GitHub. Okay, but of course, now we have a way of computing entropy, but we don't have actually anything to compute entropy on. So we took 28 healthy people in their early 30s, and we scanned them with an fMRI scan at baseline. And we asked them, how intense is your drug experience? That didn't make any sense because they hadn't had any drug yet. And we took a blood sample to make sure that there was no psilocybin in their blood. Then we gave them a pretty high dose of psilocybin. And then we fMRI scanned them again at plus 50 minutes. And we asked them, how intense is your drug experience? And we measured how much psilocin was in their blood. And then we scanned them again, 90 minutes, again at 140 minutes. And then once they were pretty much sober again, we scanned them again at about 300 minutes. So this is an overview of the subjective drug intensity over time for those 28 participants. And you can see that our baseline scan is obviously before we administer the drug. And then we have one scan on the way up, one scan at the peak, one scan as they start to come down, and one scan once they're pretty much sober again. And if you want an idea of what it's like to be in an fMRI scanner while high on psilocybin, I have this lovely quote from one of our participants who said, I felt a sense of no longer being connected to my own body. The MRI scanner and I stepped into a different reality together with colors and shapes and figures. And then she drew this wonderful picture for us. Okay, so I'd like to also pause and say that although we feel like our paper is expanding on the field, it's very important that we wouldn't be doing this work if it wasn't for all those 12 studies before us. So it's not to say that they did anything wrong. I think what they did is really good and inspirational, and it's why I am where I am now. So with that said, I want to describe the ways in which I think our study improves on the previous work. So previous work was almost entirely investigating intravenously administered psilocybin or LSD or ayahuasca. And both of these have a bit problematic when it comes to the clinical implementation of psychedelics, because the IV administration route is quite rare. It might have a sort of different, because it has different pharmacokinetics, it might have different neurological effects. And then ayahuasca is a very, it has a lot of different drugs in it. And so it's very difficult to know exactly what you're giving. We gave oral psilocybin, which is the standard way of giving psychedelics in the clinic these days. Previous studies employed quite small sample sizes. Ours is less small. I wouldn't say it's big, but it was definitely bigger than all the previous studies. Previous studies just did baseline versus drug scans. We quantified the level of drug in the blood, and then because we did multiple post-drug scans, we can do what's called association statistics, where we say how much does the entropy change as how much is the entropy associated with the level of drug in the blood, instead of just comparing drug versus no drug or drug versus placebo. Also, all the previous papers have employed a single entropy metric, and we, of course, apply all 13 to our data set. Okay, so what questions did we have? Well, the first one was whether all 13 of these different entropy metrics were actually just like the image on the left here, everyone kind of measuring the same thing, like the same central construct, but using slightly different mathematical tools for getting there. And that could be one scenario. And the other scenario is that they're actually measuring totally different things. Like each person is measuring a different fundamental feature of brain function. And then the second question is, well, which of these entropy metrics are most closely associated with the psychedelic effects? And here we're in the field of are the previous results replicable? Because we're using different data, but exactly the same analysis framework. Yeah. So what did we find? Well, the first major finding was that there was extremely limited correlation between the entropy metrics. And so at first glance, I feel like this seems like a bit of a bummer. This seems like a bit of a negative finding, that we're all measuring different things. So we've actually had no real replication, even from the generalizability point of view, because each of these is measuring different things. On the other hand, it's kind of interesting and exciting because now we have actually 13 different interpretations of brain activity that we can play with, and then we can interpret them in separate ways. So in a way, our space is bigger, but it's a little sad because we don't have the replication that we maybe thought we previously had. Yeah. This correlogram here pretty much just shows any correlations between these metrics, and you can see most of them are non-significant, and these ones are probably spurious. Okay, so now to get into the meat of the entropy quantifications, can I quickly check how much time I have to keep talking? Does someone have a meter on that? No? I'll just keep talking. Someone tell me at some point how much time I have left. So I told you there's these 13 different entropy metrics. The first group of them refer to the entropy of the static connectivity matrix. And I like to think of this as like these castellas that they make in Barcelona, where it's like a static structure. And then you look at it and you say, okay, this is pretty entropic. This is not so chaotic. This is a very simple structure. This is a very distributed structure. But it's static. And you take this by taking the whole scan and looking at all of them. Don't worry too much about what these metrics are specifically, but I just want to walk you through the general format of these plots. So the entropy is on the y-axis, and the units I wouldn't worry about. The x-axis is the plasma psilocin level, so how much psilocin is in the blood at any given time. And then the color of the dots represents how long it has been since the drug was given. So the black dots are the pre-drugs, and then the dark purples are the early scan, the light pinks are the late scan, and then the oranges are that 300-minute scan. So for these three metrics, degree distribution, von Neumann entropy, and out-network connectivity, we see no association between the plasma psilocin levels and the brain entropy measures. However, for this metric, called path length distribution, we see a statistically significant but kind of weak association between the plasma drug levels and this entropy metric. So nevertheless, I think it's quite interesting. Sorry, there's something in the chat. Okay, 25 minutes. That's great. The question that is asked of path length entropy is how diverse is the connectivity pathing across the whole brain? So here's what you do. You take your functional connectivity time series and you represent if two regions have a strong connectivity, you draw a line between them. And if they don't have a strong connectivity between them, you don't draw a line between them. And then you get these connectivity graphs, which represent, say, this is the posterior cingulate cortex, this is the orbital frontal cortex. Those things are super correlated with each other. But for example, the posterior cingulate cortex and the visual cortex might not be directly associated with each other, but they're both associated with the temporoparietal junction. Right? Then you calculate what's called the path length between every pair. So if I want to go from 3 to 2, I go 1, 2, 3. So the path length is 3, and you do that for every pair. So from every node to every other node. Then you plot a histogram of the path lengths for every pair across the entire brain. So you can see that for the left-hand graph here, pretty much everything takes 2 steps, and a couple of things take 1 step. Whereas for this right-hand one, it's a little more complex. Some things take 1 step, some things take 2 steps, some take 3, and some even take 4 steps. Then we apply that entropy formula that I discussed before to that histogram, and then you get the entropy score. And for the entropy score for the right one here would be higher because we have a wider histogram. So how do we interpret this? If this is a low entropy, you've only either got short path lengths or long path lengths, but your histogram is narrow. If this is high, then you have a wide histogram where you have some short, some medium, and some long. And remember that as the plasma psilocin increases, as there's more drug on board, the path length distribution entropy increases. So we get a more complex network structure as far as path length is concerned. Right. So the next group of entropy metrics are called dynamic connectivity, which I kind of think of as like a ceilidh. I'm Scottish, so it's like a dance where sometimes two people are dancing together, then they're dancing with other people, and it's how the connectivity changes over the course of time. And there's 6 entropy metrics in this category. 5 of them show no association with plasma psilocin levels. That's a little disappointing. However, one of them, called dynamic conditional correlation entropy, is really strongly associated with plasma drug levels. It's actually pretty much the strongest correlation I've ever seen in fMRI for like without a task. So I'm particularly intrigued by this entropy measure. I didn't come up with it myself. When we look at this graph, you can see that this is within the default mode network. So we're separating the entropy into networks. And yeah, we can see that within the default mode network, the association is very strong. But then if we zoom out a little bit and we look at the entire brain, you can see that there's this association across the entire brain. The stars represent how significant the association is, except within the motor cortex, which we can sort of post hoc be like, oh yeah, because when you're high, you can still kind of move your limbs, but you can't, for example, do default mode things. So this entropy metric measures how diverse the connectivity is between 2 regions across the length of the scan. This is a little schematic of how this works. So the first thing you do is you group the brain into brain regions using an atlas. Then you calculate using what's called a GARCH framework. It's some advanced economics maths, the instantaneous correlation between each pair of regions at every time point. Then you look over that time series of the connectivity between those 2 regions. And again, you plot a histogram of how that connectivity varies over the course of the entire scan. And then we just see again, how wide is that histogram using the Shannon entropy calculation. I can't really see whether you guys are nodding or shaking your heads or falling asleep, but I'm going to hope that this is generally making sense. Please stop me if I'm totally losing everyone. Yes. So if this entropy is low, it means that you've got region pairs that are either always connected, always disconnected, or always anti-connected, right? Whereas if this is high, it means that your region pairs, sometimes the people are, strongly connected, they're dancing together, sometimes they're dancing with someone else, sometimes they're anti-dancing. I don't know, the analogy kind of fell through there. Yes, and so what we saw, just to rehash this, is that when the plasma drug levels are low, this entropy is low, but when the plasma drug levels are high, this entropy metric is high as well, with a pretty strong correlation across the entire brain. Okay, the final group of entropy metrics I wanted to discuss with you are the regional dynamics. And here we're no longer looking at connectivity, we're no longer looking at how brain regions play with each other, we're looking at how the signal within any given region varies over time. So for 2 of them, we don't really see any association, and I'm just going to let them fade into the distance. But for this one, and to me, this is maybe the most exciting finding, called sample entropy, we see a positive association at what's called scale 1, and we see a negative association at what's called scale 5 for relatively the same entropy metric. And this metric is a measure of how predictable the signal in each network is. So again, I showed you plots from one representative network, but we can see that at scale 1, we see increases in entropy. This is the slope, this angle here, where this would be neutral, and if it's above that, it means it's a positive slope. And then at scale 5, it's got a decrease in entropy. Where scale 1 represents the raw signal, and scale 5 represents the signal but compressed in time. Basic interpretation of this, if the entropy is low, it means that the brain activity is predictable and repeats a lot. And if it's high, it means that the brain activity is unpredictable. So we can say that if you look at a short scale, okay, I'm going to go into how the multi-scale thing works. So scale 1 is just the raw time series, or the raw series of numbers. Scale 2, you take the mean of each 2-number block. And scale 5, you take the mean of each 5-number block. So you can see how that sort of compresses down the time series. And remember that at scale 1, it's increased, and at scale 5, the entropy is decreased. So it's like the signal becomes highly entropic on a tight time scale, but if you zoom out and look at how the brain activity fluctuates on a smoother, more compressed way, you can see that it's actually less entropic than when people are sober. It takes a little while. I'm still wrapping my head around it myself, to be honest. Okay, so as I mentioned at the start, there's 12 different papers that evaluated brain entropy, fMRI brain entropy with psychedelics. So we need to compare, of course, how our findings compare to those. So what we can see is that for the static connectivity measures, those ones like the towers in Barcelona, the original findings all pretty much showed an increase, but our findings don't show any association. Psi effects is psilocybin effects. Except for this path length distribution where we show the same findings previously. For the dynamic connectivity, there's 2 metrics in the previous work that did show an increase, and we don't replicate either of those. I didn't talk about this, but we can if we have some more time. But for the dynamic conditional correlation distribution, this one about how the connectivity changes over time, they didn't see any persisting effect in this, but we see a very strong acute effect in this. Finally, for the dynamic activity, for the multi-scale sample entropy, this predictability of the signal, we show the same thing as they showed before: increase at the short scale and a decrease at the long scale. And then this bold complexity measure, we don't replicate, but we show a weak association with a variant. Okay, so 2 out of 12 of the results were replicable. But then we expanded on our findings, trying to find out whether our results were robust to different pre-processing pipelines. I'm going to go very quickly through this because it's really technical, but if someone wants to talk about pre-processing in fMRI, we can do that. So we had our original pre-proc pipeline, and then we ran it again. So we ran all of these analyses again using the common atlas, narrow bandpass filters, global signal progression, strict scrubbing, without using a low-pass filter, 24 motion parameters, and not doing any scrubbing. And this is the most headache-inducing figure I have ever created in my life. The takeaway is that some of the metrics are robust to pre-processing pipelines, and lots of them are not. Again, we can talk about that if you like. Okay, so one of my goals with this project was to create this brain entropy toolbox and have it be widely available for people to use to apply to their own data. And I'm very happy that people out there in the space, like David, Pablo, Xavier, and Parker, have reached out, and they've now been applying this toolbox to their own data. And that's yielded some pretty interesting findings. We have a new data set from Basel, where this has been applied, and it shows, again, hey, increases in sample entropy at the short scale, increases in dynamic conditional correlation across the brain, except within the motor cortex, and then increases in the path length distribution as well, and some others. So it's really exciting, and I'm very glad that the tool is being put out there and that people are using it. Okay, so some conclusions. We have been doing psychedelic neuroscience with fMRI for now 12 years, and there are a lot of wonderful papers out there, but I really think it's time that we move from this hypothesis generation phase of doing novel analyses on our data into a hypothesis testing phase, where we look at what people have done previously, and we try and evaluate whether that holds using bigger data sets and more robust data analysis strategies. We also need to start evaluating the hypotheses in more depth. So, maybe, one thing that psychedelics do is they make you less likely to fall asleep, right? They increase your sort of wakefulness state. Maybe, cocaine, amphetamine, caffeine would also increase brain entropy. We don't know. So we need to also have positive and negative controls in our research to evaluate whether these effects are specific to psychedelics, because that's what we're interested in. can they be blocked with antagonists? Are they mediated by the 2A receptor, the 1A receptor, 2C? And also, we want to evaluate how robust these metrics are by doing an even more comprehensive evaluation of different pre-processing pipelines. And I think as scientists in this space, we need to sort of stand up when articles are published in Time magazine that say, here's what LSD does to the brain, because we are so not there. Like the description of what happens here was in a very small sample and using a method that no one else has ever used. And it wasn't bad, it's just not, here's what LSD does to the brain. There's been some really nice initiatives from the other groups in terms of data sharing, people sharing their imaging data and allowing other people to analyze it. But I think we should also complement that by sharing our methods more comprehensively to allow people to use the same methods on new data. I like to think also that, as well as just being critical of the whole field and where it's been, we propose some promising biomarkers here. This increase in path length distribution is a replication from an ayahuasca data set. So a totally different drug, and yet we also see the same effect. The DCC correlation is among the strongest correlations ever seen in fMRI or pharmaco-fMRI, as well as these changes in short and long-term scale predictability are also replication and have now been shown again in an even larger LSD dataset. I'd also like to emphasize that I am a psychedelic neuroscientist, but I'm also just a neuroscientist. I'm interested in how the brain works. And I think that if we can start to apply these methods and use psychedelics as a tool for understanding the brain, the implications go way beyond psychedelic science. These goes into understanding how the brain works fundamentally. Okay, with that, I'd like to thank this enormous team of people who collected the data, managed the data, analyzed the data, wrote code, and looked after participants. And I'd like to end with this quote from one of our participants. And this is a thought that he had when he was inside the scanner. He said, I think it's absurd that we try to examine this phenomenon, that we're scanning my brain to figure out what's happening. I know that we can't understand it, that we can't put an equation on it and figure it out. I feel it is human arrogance trying to tame all the beauty. I think, scan me then. We won't get any closer to the truth. And I like to think that we're starting to prove this guy wrong. And I'd love to take any of your questions about that.
Okay.
I can't hear you guys if anything is happening out there in the void.
You just got a loud applause.
Oh,
as you announced, we will be taking your questions. Just raise your hand and we'll come to you with a microphone, and Drummond will be able to hear you through the microphone.
Hi. First of all, really great, really interesting. I asked myself how, or like, did the probants already have psilocybin before in their lives when they were administered?
That's a good question. About a third of our participants has had psilocybin before in their life. We didn't see any real differences. I didn't look at the entropy in particular, but in terms of the acute drug effects, people who had the drug before reported slightly more muted drug effects. But these are all on subjective rating scales, right? So it's sort of where 0 is not very high and 10 is very high. And different people have different interpretations of what very high is. So yeah, what was there something in particular that you thought would be impacted by previous experience with psychedelics?
No, not very much. It was just very interesting to hear. Thank you.
No, no worries. Our latest study is a big study in people who've never tried psychedelics before. So we're taking 120 people who are totally psychedelic and MDMA naive, and then giving them big psychedelic experiences and seeing what changes in their brain, baseline versus 1 month. But that's a whole different study that I can talk about if people are interested.
Yeah, thank you. I can echo the previous question. It was a great talk. Thank you very much. Really, really interesting. I had a question about the long-term goal of this. I think you presented this as a potential cure for psychiatric illnesses or conditions, right? Like depression was your first example, for example.
Yeah, I think cure is definitely going far too far with that. Depression's a really complex condition with a lot of environmental factors. I don't think we can describe anything really as a cure for depression and many other psychiatric diseases. But sorry, please continue your question.
Well, my question was that both from the observer, if you see somebody who's high, they're high, and also a person who is high knows they're high. So when you get to a clinical trial, how can you do double-blind randomized trials? Like both the experimenter and the participant knows that they did not get a placebo, for example. So also in your studies, like you administered the drug to every participant. There was no control. So maybe people just start hallucinating when you put them in a scanner 5 times within 3 hours. I don't know. So I'm just asking the methodology is like the questions are very interesting, but the methodology is so incredibly hard. So my question is what kind of future do you see in this method being applied in clinics?
Yeah, sure. I don't really. Oh God. Okay, there's lots to unwrap there. On the placebo thing, I agree. There is no reasonable point, I don't think, in using a placebo except to just test check the test retest variability or time of day effects in the study. You're right. We can tell very quickly whether someone is high or not. Actually, we had a participant in yesterday that we couldn't tell for the first 3 or 4 hours, but eventually we could tell. I think it's important to go into these studies double-blinded so that you prepare the participants in the same way, whether they're getting placebo or psilocybin. You can imagine that if you knew someone was going to get placebo, you might not prepare them as in-depth. You might not give them as much care and attention. And so it's nice to stay blinded for as long as possible to try and keep the experimental conditions otherwise as similar as possible. Yes, in this study, you're right that we didn't have a control condition who we just scanned 5 times over the course of the day. That's why we rated, and instead of just looking at whether it changed from later to earlier using time on our x-axis, we actually use subjective drug intensity or plasma psilocin levels. So we're getting directly into either a measure of the mind or of the physiology of the person. Yes. Then you mentioned clinical applications and reusability of this. So on the first point of reusability, we've published this as an open access GitHub toolbox, where if you have fMRI data that's pre-processed, which is a bit of an ask, you can just point our toolbox at your data and it will give you all of these entropy metrics without you having to understand anything about the maths of how they're calculated. And that was part of the goal of this project, was to make these mathematically possibly complex, no pun intended, metrics accessible to people who don't necessarily have a background in complexity science or information theory. Finally, you mentioned clinical application of this. I don't think that this is the sort of thing that would ever be used to steer a population, like steer a clinical development pipeline or steer whether someone gets LSD or psilocybin or anything like that. I see this more as a way of understanding the brain and doing fundamental basic science, which will in turn help us to understand how the brain works, which in the long run will allow us to develop better therapeutics and neurointerface devices and so on and so forth.
Right on. Thank you very much. Good luck with your PhD.
Thank you.
Hi, thanks for your time today. A question I had is, are you necessarily looking for a positive correlation between entropy and psilocybin levels?
So I'd like to, if I'm the perfect scientist, right? I'm just out here just trying to look at things, and whether they're positive, negative, no effect, it makes no odds to me, right? Because I'm just trying to find truth. And that would be really cool if I was that, if I was that well secure in my position that I could be so unbiased with respect to my findings. In terms of my intention, to me, it is just as exciting. I just hop back. To me, it's just as exciting. Oh my gosh. to find these ones that don't replicate, because then I can be like, hey, don't bother trying to do this entropy metric again. But if all of them were not associated with side effects and it was just a total gray wash, that would obviously be a little bit sad and a little bit like harder to publish, I guess. So in a sense, I can acknowledge that I would like a publishable paper, and so I would like there to be positive associations. Is that your question? I don't really understand.
My question is, how do we, I mean, I feel like we inherently know that if we take psychedelics, there would probably be more brain entropy, I guess. But with like why exactly is that? That's my question.
I mean, I would say, how to politically, I don't understand how you can. Okay, a couple questions. First one is like, where did this intrinsic knowledge of brain entropy come from? Like, is it because Robin said it in some talks? That's like where this all comes from. I don't know. I mean, you could talk about mind entropy. You could be like, my thoughts are more chaotic. The brain and the mind are, I tend to think, two sides of the same coin, but those are difficult to map onto each other. And one of the important things that I want people to maybe take away from this is that these different brain entropy metrics are very distinct from each other. And so it's almost at the point where you can't just say psychedelics increase brain entropy. You have to say something like psychedelics increase path length distribution entropy of the brain signal, or they increase edgewise dynamic conditional correlation distribution of the brain signal. Like, brain entropy as a concept is too vague to be able to just have some blanket statement saying psychedelics increase brain entropy, because in 8 out of 12 cases here, they don't.
Right. I think that's where my misunderstanding came from. I guess I thought you were looking for a correlation where I guess you're just trying to verify some consistency between these methods.
Yeah, but we are also looking for whether these metrics correlate with plasma psilocin levels and subjective drug intensity, because those are then interesting potential biomarkers for the psychedelic drug effects. Right.
Yeah. Thank you.
Thank you.
Hey, that was very well presented. I have a question regarding your correlations you present.
Is there any in particular, or?
Nothing specific, just a conceptual question.
Cool, let's leave it at this.
And maybe I missed it, but so you're correlating the psilocybin levels with the entropy.
Yeah.
Actually, wouldn't you be more interested in the experience, correlating the experience with the entropy level, or can you maybe comment on the potential lack of psilocybin effects on the experience, which is somewhat of an intermediate step then?
Yeah, I don't know if I have a figure in my extra slides, of which I have a couple. No, I don't. Okay, let me get back to it. It's a good question. It's a very good question. The quick answer is we actually did the correlation of entropy with replacing the x-axis with subjective drug intensity. So every time we took a blood sample, we asked them on a scale of 0 to 10, how intense is your subjective drug experience right now? And so you can imagine each of these dots being a point 0 to 10 on the x-axis, and we did the correlations there. And all the correlations that I've described to you as being significant were significant not only for the plasma psilocin level, but also for the subjective drug intensity. And also for a third metric, instead of looking at the plasma psilocin levels, we did some previous work using PET imaging, where we showed the relation between plasma psilocin levels and the occupancy at the 5-HT2 receptor in the brain, because we thought that maybe that's a better way of quantifying how much drug is in the brain. And so the associations that I've described to you today as being significant are significant for all three of those. However, the subjective drug intensity rating, hey, just like how intense is your experience from 0 to 10 right now, it has to be very simple because these people are often very, very high. We can't really have a conversation with them and try and get a good gauge on the different components of their highness. Especially, they're also in the scanner, right? So this is over a shitty microphone. The other thing is, especially for the psychedelic naive people, as your colleague before pointed out, people have very little sense of what is a 7 out of 10 high, what is an 8 out of 10 high. We have a lot of people who take the drug half an hour in, they're like 8, and then 10 minutes later they're like 10, and then they're just, hey, can I take back my previous 10 because I thought that I was at a 10, but now I'm actually at a 10, and then that happens again. And so upwards 10s are different from downwards 10s in a way, because people's ceiling of potential increases. And it's also reflected against like what experiences they've had previously. Yeah, so the subjective drug intensity is just really messy to measure. Yeah, so that's why we do plasma psilocin levels for the plots that I present here. But I do agree that I think it's interesting.
That makes a lot of sense. Thank you.
No worries. Thanks.
Thanks for your excellent talk. I wanted to ask something about the last slide with a summary of the entropy correlations.
This one, or the one that has like all the oh my lord.
Yeah, this one. So basically you find an association with some entropy levels with psilocybin and not with others.
Yeah.
I want to ask, could you then summarize a little bit what the eventual effect of psilocybin is on the brain in terms of entropy? Like,
yeah. So it would be really cool if these all had some kind of central construct that they all revolved around. But the takeaway is unfortunately a little bit more along the lines of saying something like brain entropy is it's nonsensical to say something like that because they're so disparate. It's like saying interesting. Like the book was interesting. It's like there's a lot of different things that could mean. It could mean it was like politically a bit or it could mean that it was engaging in a funny way. It could mean it's so the point is that, yeah, unfortunately you've activated my trap card there. Like the point is that you can't say what psychedelic effects on brain entropy are because brain entropy isn't a singular construct.
okay, thank you.
Yeah, I'm sorry. That's a kind of an obnoxious answer to your question. Yeah.
Thank you for a very data-heavy yet visually pleasing talk. I have a question that kind of dovetails in the question that was just asked, which is basically on all the different entropy quantification methods that you showed, the pre-drug entropy is quite diverse for different participants. So the range is wide, deviations are large. And I just wondered, is there something like an inherent entropy that just different people have different inherent entropies, or like a state of mind thing where, if you're in the fMRI, a thought crosses your mind, or you're depressed or you're happy, you have different entropy levels. I mean, I know it's a difficult question to answer because you literally just said that entropy doesn't equal entropy, so it's probably hard to generalize, but maybe pick one of those entropy quantification methods then.
Yeah, or pick all of them, right? But just make sure you describe the correct one when you describe it. I think that's a really, really good question. So one of the things that we're doing going forwards is that because the Copenhagen Brain Entropy Toolbox is so widely available, we're planning to apply it to large normative data sets like the Human Connectome Project, and just see whether there's a level of entropy in the brain that's sort of normal or changes with age or something like this. So whether these brain entropy metrics are useful metrics for quantitative MRI. The other thing that we're doing as part of the psilocybin study is we're looking at different naturalistic tasks. So all of these are collective and we just say, hey, close your eyes and let your mind wander. But we're also getting people to listen to music. We're getting people to do a focused attention meditation in the scanner. I know that at Zurich, you actually have some really nice meditation data of people meditating in the scanner, and you have some hypnosis data, which is really cool. We're also getting people to watch movies. We're getting people to do a bunch of naturalistic tasks. And we're going to quantify the brain entropy for all of those as well and see whether these different naturalistic tasks have cause different brain entropy levels.
Thank you.
Was that kind of what you meant in terms of your question?
Okay, with that, we'll end today's talk and the Q&A session. Again, thank you, Drummond, for taking the time and speaking us all the way from Copenhagen, I think.
Yeah.
One round of applause for Drummond.
Thank you very much.